Today I'm going to talk about an answer to this question. Can a closed cyclic system displace itself without interacting with its environment in order to do so? The answer is surprisingly yes, and in this video I'll explain a general theory as to how. This is a graph of a simple periodic function, which could be used as a general description of a system that oscillates, like a mass on a spring bouncing back and forth after the spring is shifted from its equilibrium position. This graph can be used to describe the velocity of the mass as it oscillates back and forth. Displacement is just the integration of velocity, but we know that the integration of symmetric periodic functions over some multiple of their period is zero. They have no average value, so there is no net displacement of the mass. But periodic functions having an average value in general is a better way of framing this problem or question that we're asking. Before we even start thinking of a physical interpretation of an oscillating system, we should maybe first just ask the question, how do we define a periodic function that does have an average value? In order for a periodic function to have an average value, we basically just require that there is more area of the graph on one side of the zero line than the other. As a simple example for our purposes, we'll focus on trying to make more positive area. The simplest way to give a periodic function average is to just add a constant value to it. But in terms of a physical interpretation, this means the system is no longer closed, because if this graph were representing forces acting on part of an oscillating system, it means that there's a constant force from somewhere acting on that system. So this strategy isn't helpful for creating what we want. A better strategy is to change the width of the regions above and below zero of our periodic function. If all the regions below zero are thinner than the regions above zero, our periodic function will have an average positive value. One example as to how we can achieve that is to modulate the period of our periodic function like this function does. We can see that its peaks are wider than its valleys, and this cumulative integral makes a kind of staircase. Physically, we can interpret this as an oscillation that is asymmetric, like if you were to repeatedly take 2 steps forward and then 1 step back. There are several ways you can physically create an asymmetric oscillation. One of them is through this device in this picture here. I've made other videos going into much more detail about how this thing works, but basically the curves had different curvatures. If they were separate circles and a ball bearing was going around each of them with the same speed, it would do so with a different period for each curve. So by joining the two curves together, we have effectively mixed those two frequencies into an asymmetric periodic function. But what's great about our example function is that it's explicit and continuous, which means we can apply Fourier analysis to it and approximate it with the superposition of a bunch of other simpler periodic functions. This means that we don't actually need to build some kind of exotic physical embodiment of a periodic function with an average value. We can approximate that behavior with the physical embodiments of a bunch of carefully tuned symmetric periodic functions that don't have average values. This is an example of the mathematical results of doing so up to the 24th harmonic. 24 harmonics is a lot, but we can see that not all of the AI and BI coefficients computed are as significant as others. The second last graph is the approximation of our original function with only 6 of the most significant terms, and furthermore without the average value A0. The last graph is the cumulative integration of the previous one. So we can see from this example that we can get a close enough approximation using our symmetric periodic functions to the original asymmetric periodic function, such that we recover the desired property of its average value without actually adding an average value into the approximation. And this doesn't take that many harmonics to do so. Also, that it actually is possible to design a closed system that can displace itself by vibrating forward due solely to internal motion. Because the secret sauce to this is effectively just a difference in timing between subsystems, I've come to call this an impulse drive. In the future, I'd love to test this idea through experimentation, but I probably won't have the time for about a year. A very simple physical test would be to have a bunch of unbalanced rotating shapes, like the lever arms on a clock, and have all these spinning at different harmonics on a movable platform. We could achieve the different weighting of the harmonics by just making the lever arms literally different weights. But what's truly amazing is that if that previous experiment worked, it would suggest that it's possible to engineer a brick of metamaterial such that when you apply a voltage to it, it would start to move. That's all for today. Thank you for watching.